All right, this is the 1.2 portion of the notes. This will be briefer than 1.1. We should be able to move through this pretty easily. Find domain range of the following graphs. All right, so I did not draw these great, but the intent of that graph to the left was that it was going to go no higher than y equal to 1. Okay, and we see an open circle at x equal to 3 and a closed circle at x equal to 1. That's what they were supposed to look like anyways. We can probably make the closed circle a little better. There we go. Uh, that looks like a mess. Anyways, so what is your domain? Remember, domain means possible x values, right? So let's go from -1 to 3. But it's not including 3. It is including -1, though. So your domain is from -1 to 3. And then your range, it does touch y equal to 0, goes all the way up to 1. So your range is bracket 0, 1. For the other one, your domain, it goes from -2 to 3, but not doesn't include them, so we parentheses -2, -3. Your range, what do we got for our range? We got it says at 4, so your range is just simply 4. For this next one, I'm giving you just a function in the original problem that f of x equals 3x cubed minus 10x squared plus 8x, and we want to find the x-intercept in the zeros, or excuse me, y-intercept in the zeros, okay? Or it is going to be end up being the x-intercepts, right? Are there any y-intercepts? Yes. You find the y-intercept by simply plugging 0 in for x. When you get 0, so 0, 0, so your y-intercept is in fact 0, 0. Now your zeros, factor that. I factored to over here to the right and did AC method, okay? I saw GCF first, I factor out at x, and then AC method, if you aren't familiar, I'll refresh you. That's when I take the first number, leading coefficient, which is 3, and I take the constant, which is 8, and I do 3 times 8. 3 times 8 is 24. And I think about what are some factors of 24 that add up to -10, and that's -6 and -4. So I replace -10x with -6x and -4x, and then I GCF the first pair and then the last pair. First pair, 3x. Last pair, -4. The goal is to get what's inside the parentheses to be the same. I have multiple x minus 2's now, so I factor that out, and I'm left with whatever's on the outside, which is 3x minus 4. So what are my zeros? Set them all equal to 0. It's 0, 0, because we should probably already know that because it's a y-intercept. The other one is 2, 0, and then 4 over 3, 0. I gave you kind of a brief look at what this graph may look like. All right, now we're going to test for symmetry, okay? There are 3 different types of symmetry we look for. Symmetric over the x-axis, y-axis, and origin. Over the x-axis would look maybe something like this. Okay, where it's the same function but flipped over the x-axis, hence it's symmetric, right? And you do this if you're given just a function, which we're going to get examples here in a moment. You plug in x everywhere you see an x, and a negative y everywhere you see a y, and if you simplify it, it's the same exact function, then it reflects over the x-axis. Now, y-axis. The basic one is mostly practice. I drew it out terribly. I'm sorry, it's a little bit off to the right, but it's okay. But point being, if you plug in negative x everywhere as an x and a y everywhere as y, simplify, it's the same function, it reflects over the y-axis. Origin. Most common example with origin is your x cubed functions. Or like that, right? You plug in negative x everywhere as x, negative y everywhere as a y, and simplify, and you get the same function as the original, then it reflects over the origin. Now let's try 2 examples right here. Anytime I see a squared or an even power, I am automatically thinking about the functions that have a negative with that given value. So when I see an x squared right here in this first one to the left, I'm thinking it might be reflecting over the y-axis, and then I should try that out. Not that it's going to happen every time, but in this case, it might. So let's run a negative there. Simplify, so negative x all squared. Negative times a negative is positive, so I'm just going to get that negative on the outside. Negative x squared plus 6 equals y. Is it the same function? Yes. So it reflects over the y-axis. Reflects over y-axis. Okay. It does not work for all the others, right? If I went through the others, I put negative y in for y and x in for x. That's going to flip all the values. That's different. Okay. That won't work. Same thing with the origin. That'll flip everything and make it not the same. Not good. Okay. Next one. I see x squared plus y squared equals 25. They're both squared, so I'm thinking origin. And then that's going to get us x squared plus y squared is 25. Yes, it's the same thing. Beautiful. I'm also thinking, so it could be x-axis as well. So I'm going to put in negative y everywhere. And then, yes, it works. So it is over the x-axis as well. How about the y-axis? And yeah, it works. So it reflects over the origin, x-axis, and y-axis, all three of them. How about that? Reflects over x-axis, y-axis, and origin. All three. How about that? And last thing, and then we're done. Even odd functions. Simply put, even is symmetric over the y-axis, and odd is symmetric with respect to the origin. A trick to do that is, for these functions, you're generally given an f of x equals something, right? F of x equals, let's give an example here. Let's say it's x squared, okay? What we're going to do to test it is I'm going to put in negative x everywhere there's an x, okay? And then simplify it. Just like we did with symmetry before, okay? And then we get x squared, so it's the same function. So since same function, look at your even odd rules, okay? It says even, when we put negative x everywhere there's an x, and we get the same function, it's going to be even. So in this case, it is the same function, so it's going to be even. Now, if it's everywhere is the opposite, let's say I have f of x equals x cubed plus x, and I put in negative x everywhere. That's going to give me negative x times negative x times negative x is negative x cubed minus x. And what do we see here? Everything's the opposite. Everything must be the opposite in order for it to be odd. And that's the case. So it is, in fact, an odd function. Nice. I appreciate you watching, and we'll see you in class. Bye-bye now.